Did you know that when I lifted these books just now, it takes the same amount of work as if I had lifted them like this in this really, really weird path? Now, we're not talking about work as in, wow, that was really hard work. We're using the science definition of work, which is the integral of f dot dx. So work requires displacement. So I could give you the physics explanation of how work is based on a change in energy, and the only thing that changes between 2 points is the gravitational potential energy due to a change in height, but I don't want to do that. Today, we're talking about conservative vector fields. Now, what is a vector field? A vector field is a function that maps every point in an n-dimensional space to an n-dimensional vector. So, if we were in R2, it would map every point xy in R2 to a two-dimensional vector uv, which would look something like this. Now, why do vector fields matter? Well, besides being cool and having loads of applications, there's a special property that some vector fields have called conservativity, or being conservative. There are many ways of checking if a vector field is conservative. My personal favorite is the gradient theorem, or the fundamental theorem of calculus for line integrals. But let's focus on what being conservative means instead. When a vector field is conservative, it means that the line integral through the field depends only upon the start point and the end point of the integral, and not the path itself. So, these three paths through a conservative vector field, they're all the same because they have the same start and end points. Now, let's prove that the gravitational field is conservative.
We'll simplify the gravity vector as a vector generally pointing down as close to Earth. It basically points straight down. Let's also have our function from one point to another, and this will be r of t parameterized g of t I hat and h of t j hat. The format of a field over a curve C is the integral along that curve of f dot dr, or the integral from a to b of f of r of t, as seen here, dot dr dt dt. F will be the standard negative y unit vector as seen, and our other vector is the derivative of our r of t function. Now, when we take the dot product, we get the integral from a to b of negative h of t dt, and from the fundamental theorem of calculus, we know that the integral of a derivative is f of b minus f of a, and accounting for negative signs, there's the answer you see on screen.
Cool! We just proved that work depends on height, but in a snazzy math way. Also, just so you know, even if gravity was a variable function, such as a rocket going to the moon, we could still prove that the gravitational field is conservative using this general approach. Thanks for watching. I hope this taught you about conservative vector fields and work done by gravity. Bye-bye!